Thank you, Professor, for that long and generous introduction. Carlos, Marlene, thank you for having me here today. I'd like to talk about buildings. I'm an architect, cabinet maker, teacher, and I make buildings. But I want to talk about the relationship between buildings and the planetary problems that we're currently facing, dire ones, as we all know.
Alan, sorry, you have to put the microphone.
So turn on the microphone. It's okay?
Yeah, it's okay with me. I think we're good. So, though I am an architect and I like to talk about our buildings, I'd like to talk about the architecture of other systems. Wood, which you can see from this incredible crosscut of an ash tree. All of both the things that we love about wood, that we can identify with the body. We can see the age. We can see the stresses that as I get older, I feel more and more in my own body. And the things that have made also contemporary structural engineering and building design ignore wood because it's so heterogeneous, so different in all cases, so challenging. These knots, these checks, these configurations of wood grain have made engineers in an era of homogeneous materials like steel and concrete avoid the challenges of understanding the variety and dynamism of wood to our peril. But I'm not going to talk so much about wood, as instead I'd like to talk about the architecture of the entire system by which we make buildings, and by extension cities, and all the aggregation of human settlement that exists across the planet. This starts from the extraction of material and energy from the grounds, from forests, through the transport, production, construction, operational life, and finally the demolition and disposal of buildings, the so-called building life cycle, which we haven't really thought thoroughly enough about until very recently. So as a prologue, I think we should talk about the real challenge we face in the next 25 years, quarter of a century. This is Tokyo. It's the largest contiguous urban area in the world, 5,000 square miles. I think that's around 13,000 square kilometers. 3 prefectures, home to 39 million people. But industrial ecologists, people who study the flow of materials through life cycle, product life cycles, will tell you that this is also the largest stockpile of human-made material in the world. And with that come a set of impacts to the natural systems that exist in the world and that give us the ecosystem services that we really need to survive as a species and that allow our fellow species on the planet to survive. And I'm not going to list them here, but of course, you're familiar with all of it. The conversion of natural systems, loss of biomass, raw material consumption and disposal, waste generation, water scarcity, heat island effect, and somewhere way, way down in the supply chain, possibly even human slavery. And we don't even know how to identify that, but we see it and know it's there. So this means a lot. Think in 25 years, we'll be adding 2.3 billion people to the planet's cities because of migration, because of population growth. We'll consume 3 times the land area that we currently occupy with human settlement if we continue to build with the low density morphologies of urbanism that we currently practice. That's 56,000 square miles of city. That's of a building, I should say. That's the size of New York State, 2 Irelands, 4 Bhutans, covered in a building, not a city, a single building, which is great news for all of us in the construction sector. It's worth $97 trillion of new construction. It doubles the current building stock that we have in the world. It also represents nearly half of all anthropogenic greenhouse gas emissions, 49% of which, nearly half of which, are associated with the construction or the embodied emissions. I'll get into that in a minute. But if we continue to build in the way that we do, with largely mineral classes of material, we'll blow through all guardrails that we've set up for carbon emissions on the planet and through our planetary boundaries, 71 gigatons emitted by the building sector alone. And I just want to note before I go on that the last time we were at the current concentration of CO2 in the atmosphere was about 5 million years ago, and temperatures were 5 degrees Celsius higher than they are now. So that just gives you some context. So really what I'm talking about is a relationship between the biosphere or natural systems, and we'll call it a forest for now as a stand-in, and the city, which we have spent the last, well, human history building, but really the last 200 years has been the time frame for the construction of the contemporary city. And in doing so, we've dug ourselves into a deep, deep hole and brought a lot of that material onto the surface of the planet. And that hole is both metaphorical and literal. This is a copper mine in Utah in the US. This will never be productive biological landscape ever again, except with the incredible input of energy to try to restore natural systems. And we know this life cycle. Carlos is working on it, professors are working on it, you all are working on it. It starts with the extraction of material, through the handling and transport of that material, the processing and manufacture of these high-strength products that we use to build our dense cities, the construction and maintenance and repair of those cities, and finally the demolition and, as I said, disposal of those cities. And that represents a quarter of all anthropogenic emissions, even excluding operational emissions, the consumption of energy to put the lights on, to cool our buildings or heat our buildings. And the problem is, the way we've been thinking about sustainability for much too long is that we've simply looked at it as an overall condition. You see on the right-hand side, we have operational emissions, and it looks like it has a lot greater effect than all the embodied emissions: production, transportation, construction, use, and maintenance of the materials and equipment that we put into buildings. But if you add a time frame to that, and you think about that we have only 25 years to solve this problem and use building as a potential lever to do so, you start to see the problem. Initially, with the production of material, a huge carbon spike at the very beginning of the building life cycle. And then over the course of the building life cycle, through various stages of repair and maintenance and retrofit to the end of the life of the building, we keep having pulses of emissions. And let those pulses of emissions stand in for other systemic impacts that we don't even see, that are far away in remote landscapes and ecosystems. This is what we call the conventional so-called embodied carbon of a building. And if you look at the operational emissions of a building over that lifetime of a building, you see that we never, through efficient operation of our buildings, we won't pay back that initial carbon spike from the embodied phase until well into the building life cycle. And if we make our buildings really, really efficient, as we do with, say, passive house construction, we never pay off that debt. Conventional embodied carbon will be the primary emissions that are created, what we build with, not how we operate our buildings. And then if you add in that 25-year time frame, you see that until 2050, 25 years from now, we will have only barely just paid off with our efficient buildings, which use more material, more insulation, et cetera, our embodied debt. And we never pay it off with operational carbon emissions, for the passive house operational carbon. And the most important thing for me right now, as I work with foresters and I work with urban planners and policymakers, this conception of the building life cycle does not even take into account the ecosystems that we affect when we extract material, nor does it take into account what happens to cities in their afterlives, after those buildings have been demolished. What happens to those materials? And an important piece is also that as of 2020, global biomass, the material that's biologically produced on the planet, is now outweighed by the technomass that we've created. And that's happened for a lot of reasons, a lot of different materials. But if you look, conventional concrete and all the aggregates that we use to make mineral-based materials are actually the largest producers of those emissions. So what do? We know that urban settlement creates land conversion problems. We know that land conversion, forest loss, deforestation doesn't really come from the wood products industry. Say 10 to 15% of deforestation or harvest comes from our making of products. But climate change creates disturbance. Agricultural conversion creates disturbance. Mining and mineral extraction cause deforestation. Forest product use, as I mentioned, but even just the making of our sprawling suburban landscapes. America's greatest export, actually, unfortunately, and most durable one, creates deforestation. And we haven't solved the problem of resource inequity through building. And that resource inequity is local. We can see it in any city we visit, but it's also global. And these flows of resources and these resource scarcities that exist in different places exist, of course, in the global south, which we spend a great deal of time appropriately worried about. But it also happens in cities like mine in New Haven in the so-called global north, where pockets of poverty and resource scarcity and disenfranchisement also exist that we have to solve. It's a transscalar problem. And the materials we consume, we're running out of sharp sand, an critical element in the production of reinforced concrete. We consume 40 billion tons of sharp sand per year. It produces not only buildings, but it generates syndicates, criminal syndicates that extract sand in delicate ecosystems. We produce waste. And waste is produced in buildings not just by the making of nice buildings, but the destruction of buildings in places like Kharkiv. We extract materials from the landscape, and it's not just a process, it's an economic model, extractivism. And that extractivism has impacts at the very human level that affect us if we take the time to look for it. And we're at a difficult time, especially in America, where climate denialism, climate change denialism is rampant, and it's become a political force that now runs one of the most powerful countries in the world. And when we have the person who is designated to protect the environment saying things like, we've been dumping too much money into this climate change thing and it's going to stop, we realize that that 25 years is shrinking. And we are all very familiar with this International Governmental Panel on Climate Change report, which shows these various scenarios for decarbonizing the environment. Business as usual, if we keep doing what we're doing, it's a dead end. There are certain sectors that we think we can decarbonize, energy, transportation, but that just gets us to a kind of level well above the 2-degree temperature increase that the UN has recommended that we stay below. And so what's the negative emissions scenario? What's the scenario that allows us to completely reverse climate change, or at least in part reverse climate change so we can stabilize the planet? So this brings me to the question of material classes. Steel, concrete, timber. Timber has been largely ignored as an urban building tool or material until recently. And if you look at the way we typically measure material emissions, production stage emissions by weight, you can see that concrete and timber outperform steel. They emit much less carbon in their production. But if you add in strength to weight ratio, you realize that wood, at a quarter of the weight of reinforced concrete, and offers you much more structural span, if we could put it this way, per carbon emission. And so we really have to start thinking about how engineered timber can play a role. And moreover, if you add the capacity of material to store carbon, biogenic carbon, you realize that timber much outperforms steel and concrete. Now, there are lots of problems with using wood, regulatory, in terms of the building detailing, which we'll talk about a little bit. But this is an opportunity that we need to try to capture. We don't cut trees like this anymore. At least industry doesn't cut trees like this. It's inefficient. It's hard to move. You can't saw it. So there may be some large trees that are being cut illegally in different places in the world, and that's a big important thing, and forest ecosystems that are being degraded. But we can't stop working on the problem of bio-based building just because we have a history of doing things like this. Today we have different chemistries. Yes, plastic chemistries, but also bio-based chemistries that will give us adhesives. We've been making finger joints to put small pieces of wood together into giant systems for a long time. Little sticks now we cut to produce little pieces of wood that we join together to produce enormous sections of material that are easy to work on with digital machinery. And because we're making small pieces make big pieces, we're actually able to distribute the highest quality fiber to the most critical parts of a structural member. And now we can start to use mixed species. In Europe, we used a lot of European spruce to make glulam, pine, also Douglas fir. That's in shorter and shorter supply. We had a lot of beechwood. We started making Baubücher in Germany, so beech laminated veneer lumber. And this company, Blumer Lehmann in Switzerland, is producing a 5-story building with no steel connectors, using laminated veneer lumber for dowels and bearing plates to create the connections. So we know how to take little sticks and we can put them together with dowels, nails, screws, adhesive. We can cross-laminate them or longitudinally laminate them. These produce new classes of frames and panels that we can make into large buildings. And now, according to the International Building Code, which is the reigning code in the United States and Canada and used in other places around the world. And by the way, I'll mention one of the slowest codes, building codes, to adapt to new technologies. In 5 years, we've gone from an allowable height of 6 stories to now 18 stories using engineered timber. So we have opportunities, and we have to try to capture them. But the question is, do we want to really make wood skyscrapers? When most of the world is building 5, 6, 7, 8 stories, Barcelona, considered one of the most beautiful cities in the world, 8 stories, consistently. And it is incredible that sunlight, land area, and photosynthesis, with a combination of some water, produces industrial material with really no energy inputs. We don't use fossil energies to grow trees. So the question is, really, can this incredible natural system, forests, as one example, serve in conjunction with timber building to create a circular, metabolic, regenerative system, a geotechnology that we can apply to try to draw carbon down and store it in cities? So we wrote this paper, which the professor mentioned, Buildings as a Global Carbon Sink, which was intended as a provocation. What if we built all of the buildings that we'll build in the next 25 years out of wood or other biofiber, plants, hemp, typha grasses? And what we found, working with political scientists, but also climate scientists and environmental scientists and material industrial ecologists and foresters, that if we were to do that across the planet, we would actually completely reverse climate carbon emissions. So instead of emitting 71 gigatons of carbon, we would actually be storing 60,000 tons of carbon. So we eliminated suddenly this huge carbon spike. And of course, that created all sorts of arguments from a lot of people, justifiably. It was intended as a provocation. It had not really been discussed at that global scale. And this is really the framework that I'd like to give to you. Forests are dynamic systems. They grow, and as they grow, they absorb carbon. They're also harvested or they're disturbed naturally by forest fire, wind, etc. And we can understand how much carbon is stored in that regenerative cycle of forest growth and death, but we can also imagine what would happen if we were to transfer that material out of the forest before it rots, before it emits its carbon, and put it into buildings. Yes, we know how to build low-rise buildings, but we can actually now put them into cities. And if you look below this ground line, which is a sort of carbon transect, a measuring point, we start to see the amazing amount of carbon that we can store when we build dense cities out of biomaterials. So this is where I'm going to talk a little bit about architecture, my practice, Goa. We started using timber. I was a cabinet maker, a furniture maker, and carpenter, and went to architecture school and took that design build practice into our architecture practice. And some of the first projects we made with engineered wood weren't buildings, they were bridges and temporary structures. And we perfected the industrial processes that make things like glue laminated timber and how to start to manipulate those industrial processes with just little tweaks so that we could get more and more enduring, rich kinds of structures. And mostly we were working in remote landscapes, parks, recreation areas, etc., to make these buildings. And now we're starting to bring them more and more into urban areas or more urbanized areas. Along the Hudson River, where we're building a 450-foot timber, steel, and concrete hybrid bridge to allow citizens to cross over the industrial landscapes that we've created that have separated us from natural places like the Hudson River. And this reconnection is part of the story of bringing timber back into the landscape. And we built schools using timber. Schools also that are geared to teach people how to use timber in natural systems. Common Ground School in New Haven, in my town, was built by 5 carpenters, prefabricated in a factory, assembled by 5 carpenters in a quarter of the time it took to make just the concrete foundations. All prefabricated components, completely modularized to produce a school for kids who have very little exposure to natural systems. And it was really interesting. I would ask the students, what was your favorite part of the building? You know, hoping that they would say, oh, it's really a cool looking shape, or we love the daylight, or it works really well going from classes to classes. But they always said one thing, which was really surprising to me. They said, this building smells good, which I think is a great criteria to take back to your design studios. Make your buildings smell good. And the other point was that most of these students, because they study environmental science in their high school program, they know where that wood came from in Quebec, almost to the point on a map. They could identify where that particular wood was harvested. But nobody, not even I, and I study this stuff, can tell you where the gypsum was mined to make the wall paneling. And so this building, in a sense, became a kind of model for how we thought about the use of materials, an entirely bio-based material that this 14-year-old high school student could calculate exactly how much carbon was in all of the materials that were used to make the building, and discovered that the building actually offset 100 cars' annual emissions, which made the building truly net zero because it offset the operational emissions and the other embodied emissions for 10 years. So at 10 years, this building had emitted no carbon. Production, manufacture, transport, nothing. It was offset by storage. And not only that, we learned we could track the chain of custody of all the trees, how much carbon was stored in the land, both above ground and below ground in the soils. You know, when was it best to cut these trees? How much carbon was emitted when we cut the tree because of drying of land? How much was stored in the building? How much could be put into these different kinds of products? And how do we map that onto a building? And in all of that calculation, what some of us call life cycle assessment, we were actually using life cycle design as a strategy to store carbon in the buildings we made rather than emit it. And then we took this on the road. We made a building, the professor mentioned, the ecological living module, elm, which is the name of a tree species, which is particularly famous in the city of New Haven, all killed by Dutch elm disease about 70, 80 years ago. And we made the elm as a fully self-sustaining bio-based building for 4 people, 200 square meters, and we put it in the middle of the UN Plaza in New York. Designed in 8 weeks, constructed in 5, installed in 3 days. And imagine taking a building, I don't know if any of you have ever been to the UN in New York, but it's like going through airport security, but with a building. Fully integrated living systems for a family of 4 in precarious urban settlements. Fully passive systems for energy, heat, air conditioning, lighting. Micro-farming as a possibility, both for sustenance, but also for sales and a commercial process. Energy production at all different scales. And it brought 3,500 people, 3,500 people from all around the world through this little tiny building. And many of them said, the New Yorkers especially, this is much nicer than my apartment. And they'd happily live there. And a lot of people loved being associated with it, including the head of the United Nations Environment Program. So we thought, oh, we need to bring these technologies to the city. And in the city of New Haven, where I live, a little bit like Lisbon, much smaller, there's a lot of beautiful historic building, but not a lot of good land area to build in. We're population rich, land starved. And so we started to take historic buildings and to overbuild on top of them, using these light, stiff structural systems, cross-laminated timber and glulam, to produce housing that existed on top of existing non-reinforced masonry buildings. Brick buildings with no steel reinforcement that you couldn't build on top of with steel or concrete because of the combined weight and the lack of stiffness. And so we're just finishing a project in New Haven where we have a 7-story shaft for elevator and stairs that carries up onto the top of a 4-story building to add 2 stories of housing, nearly doubling the housing area, using this shaft with no reinforcement to the historic structure because the building and the shaft lock the whole building into the ground. 7 stories of CLT to produce a tree trunk that takes it down to the foundations. And so this is the kind of work we're doing all over our city because developers are not allowed to tear down historic structures. They don't know how to reuse them, and our goal is to try to save those structures through circular economic principles and add to them using bio-based economic principles. And then the big question, well, is it less expensive? Well, not yet, because it's early on, but we proved that you could build an entirely wood-engineered building, massive construction, to make it an affordable housing for people who live well below the area median income in the US, the most disenfranchised populations, who hope to build high-quality, healthy housing for. And we proved that it was almost as cheap as the cheapest construction system for a 4-story building in the US. And then we doubled down and we pushed to use entirely bio-based materials, which is absolutely not the way that we build buildings in the US. And we worked hard to understand all of the critical alignments that make it a different kind of construction system than using a frame construction, and how we could get the highest performing assemblies out of that for operational efficiency using bio-based materials, and prove that we could create airtight, insect-proof, high insulation buildings that performed really well at the highest standard. And this building is under construction now, nearly finished, 4 stories of housing. It'll house 80 homes for this group. And all the things that we learned about how you ship material, how you get it through customs, how you actually call a crane and get it to be assembled on demand so it's quick. All of the mistakes that we could have made were learned here, and we're bringing it back to several more of these kinds of projects in the northeastern United States. And the building is lovely. And you realize that upstream environmental health accords with downstream public health. And that's the goal, to try to link those two systems with a whole host of purposes and reasons. Which brings me to a really important question that was asked of us when we wrote this paper. What happens to all the forests if we build all the buildings in the world out of wood? We're going to ruin the forests. So these questions are first and foremost in our work now. I used to be a big advocate of engineered wood. Now I'm a big advocate of engineered wood, but only if we can protect our forests in the process, or even improve their health, which is the big question of regenerative design and building. And I also remind you, when we ask the big question about forests, our forests are under stress right now, and we're also emitting a lot of carbon, so we don't have a solution if we don't use forests well. That's a really important part of this conversation. And we can tell you a fact, and the fact is, all forests across the planet, even across our region, are different. They're dynamic, varied systems, each with their own set of problems and their own set of ecosystems. At the stand scale, you can see it in the forest where I live. Different tree types mixed in, so-called hardwoods, broadleaf species, deciduous and coniferous species, different age classes. If you go to the Pacific Northwest in the US, Douglas fir forests, a little more regular. The boreal forests of Canada and Russia are different. Even the plantations in the southern United States are different. And plantations aren't all bad. If you build on disturbed landscapes, degraded landscapes, and you plant trees, it produces ecosystems, maybe not as rich as the indigenous forest, but it produces ecosystems. And we know that's true also in Austria and other parts of Europe, Finland, and even in Bhutan, where the mix of forests are incredibly diverse, and the challenges of these steep slopes in the Himalayas make processing challenging. And for those of us who are really concerned about ecosystem disturbance, forest fires, we're losing forest stocks. Forests are now sources of emissions more than they are carbon sinks, which is really horrifying. It's important to remember that we have strategies for addressing this. And people have looked at this carefully. Colleagues at the Yale Forest School, where I work, have looked at this carefully, and they've compared the no-harvest strategy, which is just let forests be. Leave them alone, guys. Keep building with steel and concrete. The second is that we teach our foresters to use techniques that regenerate forest health rather than leave them vulnerable to things like this. And then finally, one strategy was to look at regenerative silvicultural treatment incentivized by creating building products. And that really proved to be the most intriguing one, because it was different across different classes of forests and areas, but it was consistently produced a deeper and more durable forest carbon sink if we could incentivize these treatments and pay for them because we were making products out of the material. So my friend Jamie Lawrence at the Climate Smart Forest Economy program not too far in León, Spain, said this. Look, simple. We have to stop telling forests that we want a particular grade, species, diameter of tree, and we have to learn what the forest can give us, and we'll start to create responsive structures. We have to think as designers, engineers, architects, builders, what foresters do when they try to regenerate a forest. They think about, what do I do to enhance biodiversity? What do I do to control disease? What do I do in this forest to prevent forest fire or store more carbon both above ground and below ground over the forest life cycle? How do we improve water quality? We need good water quality. Forests provide that to us. What about controlling invasive species now that we live in a global transport economy? And finally, how do we make the soils better for the planet using forestry? We could be asking these questions. We just don't talk to foresters, so we need to start doing that. So I'm here today advocating a kind of design approach which is more than the life cycle approach. It's more than trying to design ecosystems, which we can't do. We'll never be as efficient as Mother Nature in designing ecosystems. But to think ecosystemically as we design. Think about circularity. Biocircularity is one example. I've talked about trees, but what about bamboo, the great work that's being done here? Or tifa grasses from peatlands. If we were to actually restore the peatlands that exist in Europe, we would dramatically reduce carbon emissions. And to do that, to re-wet peatlands from agricultural land, We need to create products that incentivize that. So that's really, really critical too. Our role is to tell people how to use this material in creative, durable, functional ways. We generate waste. We know that. The construction sector produces 71% of the waste on the planet. But we can use the systems by which we collect that material and reuse it. Circularity is, we can't solve the problem with trees alone. We have to use the industrial waste flows, the consumer waste flows, the construction waste flows that generate so much material waste and loss. And we have to do it not only through thinking of cool ways to apply the waste to your building, but actually imagining that the buildings you make will be material banks for some future flow of new raw material, rather than cutting down forests, digging up the ground, carving into the lithosphere. We have to learn how to handle it. We need to consider ways in which we can make larger single elements simpler so that we can disassemble buildings, how to make them safe for human use in case that they might carry some kind of toxin in them from their previous life, and apply them to building so that we get really high performance buildings. We need to think about where the waste comes from. In Berlin, a huge amount of waste is, in terms of weight, comes out of the mining industry for aggregates for road construction and from construction sites. It's earth, and we pile it across landscapes to store it, and we try to move it, and it's really heavy, and it's really energy and emissions intensive to do so. So could we start to study that soil waste, the so-called waste, take it apart and reconstitute it into materials without cement, without firing, in this case, entirely earth-based bricks, and get the approvals to build a 3 or 4 story building structurally out of these materials. And we have that. We have a DIN certification through Bauhaus Earth from the German government. And we have to develop scenarios for reuse. We can't just build good buildings that can be taken apart. We have to show how they're taken apart, and we have to project, perhaps 60 years from now, how those buildings will be distributed into new product classes, and how that process particularly works. Even though it's hard to predict what happens next week, let alone what will happen in 60 years, but that has to be part of that design process. And finally, most importantly, and the very first thing we need to do is stop tearing down our buildings. We're the most creative people in the world, truly. Architects and engineers and builders orchestrate huge numbers of people, a lot of material to produce these buildings, these very large consumer products that we make, buildings. And we have to stop tearing them down, especially if we can't prove that the building that replaces the buildings we tear down absorbs and reduces embodied carbon. And it's not just the beautiful historic buildings that we have to protect. We have to protect the buildings we don't love, like the New Haven Coliseum, 4 stories of parking, 66 stories above the ground, which everyone hated. And this is what we did to it 10 years ago. We tore it down. 6 acres of building, steel, concrete, gone. Shipped in part to China and Asia for the reuse of the steel. The aggregate was trucked out and dumped in landfill. We have to change not only the material densities and types that we use, we have to change the urban morphologies by which we build. This is America. America is covered with this kind of stuff. But if you aggregate it into dense housing, it covers one tiny portion of one of the states of the US. So this sprawl has to stop. Convivial density of the buildings and the urban spaces we make has to combine with material density to produce all of the advantages of shared resources, concentrated infrastructures, efficient mobility services that we can now afford because we have dense populations, reduced environmental impact from remote sites, and finally, I think healthy communities. And I don't need to be telling a European this, but come to the United States and see the kinds of low-cost building that we're doing that consume land area, and you'll understand why I'm making this point. It can't just be bio-based material. And we have to stop thinking about just government, country or state or province by province. We have to think across those borders. We have to think about the way in which we can break the unhealthy relationship between mineral-based, high emissions intensive construction techniques and materials that go into dense cities, and this relationship between forest land and cheap, low density building. And the way to do it is not to think in the state of Connecticut, where I live, where we don't have a lot of forests that we can use for buildings. We have to think regionally. We have to look at the woodsheds that exist, or any material shed, circular waste material sheds. We have to look at the demand centers. And we have to think about all of the capacities and how those different species are moved specifically into specific industries to produce high quality buildings and map that. We have to track it, and we have to tell the rest of the world how to do it. And we have to look not just at the aesthetics of the wood, because we like wood because it's pretty. We have to think about its specific properties and how that can be transformed into assemblies that work for people who have to live in them, and builders who have to make them, and owners who have to preserve them. This means a lot of workforce opportunity in rural areas all around the world, as it does both high and low tech construction processes and urban employment and enterprise opportunity in our cities. And what this gives us is a whole new economic paradigm where we care about the health of our natural systems because they're producing products that drive our economy and our social welfare. This rural-urban synergy is something we do not have. In the US, one of the reasons Donald Trump is now the president is because rural areas and urban areas, whether it's in a state or across the country, and sometimes even within a town, are not speaking to one another. We do not have a synergistic relationship politically, materially, or economically. If we build in localized areas with localized materials, we will reduce those huge transport impacts that the policymakers now at the international level are trying to decarbonize. And we can see the feedback mechanisms that we need to understand how our forests or our rural landscapes are doing. Those ecosystems, we need to have the feedback mechanism. And if I'm building with material from Brazil, I have no idea, no matter what fair trade group tells me is feasible. And finally, we have to think about system finance, not just at the state level or even national level, but globally. And I'll talk a little bit more about that in a minute. Oh, I'm going backwards, sorry. And this is important for all of us because all of us are working on this problem, I know, at architecture schools and engineering schools and vocational training around the world. We need to start teaching people differently. We have to have criteria that's not just disciplinary, it's not only interdisciplinary, it is systemic. We have to think fully. Like these students of mine who are architects, who were brought into the forest by a forester and analyzed the forest and found that this forest was a degraded vineland and that they could actually harvest trees from that degraded vineland that were low performing, not so healthy trees to support the better trees in the forest and turn those into structural components through material testing and performance analysis, through studio design techniques that you're all familiar with that really focus on the integration of these new materials into buildings, through the kind of advocacy that teaches our regulators and our governors and our planners how to actually implement these materials, how we detail them so that they are preserved, and how we produce buildings that are meaningful to the people and that tell the story a bit about the work that we're doing with these new materials. So I'm going to wrap up. You've been very patient with me. I really appreciate it. I want to say a couple of things. Right now, because of the way our economy works, and I can say this nearly globally, that advanced capitalism has produced a set of processes and behaviors which we've become accustomed to that we have to break. And our investors have to stop focusing on new technologies, hydrogen steel, carbon capture, photovoltaic energy production, bioenergy. Let's burn all this wood so that we can get energy so that we don't have to use fossil fuels. Maybe not so great a solution. And yes, not just mass timber. That's not enough. Massive Holz will not answer the world's problems either. but we're we're avid technologists. We want to use cool technologies, and financiers like that really clear bucket of product that they're going to get and the associated revenue streams that they're going to get by investing in one technology and not thinking systemically. And we need to make systemic interventions. We need to really start to think about how we invest in nature, because that is our primary infrastructure. And there's no big return that we can see. These are considered externalities that we need to address. And we need to learn how to value how much it means to the world, or even our project, if we lose a species on the planet. How much does that cost? How much does 1 degree temperature rise cost? And how could we possibly assign responsibility to a single actor building one building for the large terrestrial impacts that we're creating? These are really important problems, but we have to solve them. How do we restore entire ecosystems through the building plan that we have? Or how can we transparently assess those impacts across the system and tell that story honestly and transparently? It's really important. If we're making all these claims, and architects, as you well know, make lots of claims for their buildings, I say prove it. And prove it not just to celebrate how brilliant you are, but to show how the system breaks down at certain points so that we can correct that. And finally, we need to end the idea of waste altogether. And that's a systemic problem, both in how we conceive of things and how we act upon them. Keep going the wrong way, I apologize. So, as a friend of mine, an environmental chemist, Paul Anastas, very famous guy, developed the principles of green chemistry, said, we have to distinguish between circumstantial barriers, the things that get in our way. We don't know enough. We don't have enough data. Well, we've already put all this money into the system, and we have to recover it. Analyzing within the project site or the development pro forma rather than thinking across landscapes and across disciplines. Yes, the markets don't know how to handle this yet and value it, but we can solve that through design. Foresters think one way, architects think another way, engineers think another way. We've seen those challenges. We break down those silos between disciplines. And finally, the builders who we work with, they don't really know how to handle these new materials, and they're used to doing this with steel and concrete. Well, we can train them and we can change those behaviors if we can argue for the benefits. What we really need to do, as Paul Anastas, my environmental engineering and chemist friend, says, is capture the intrinsic benefits. We're looking for intrinsic benefits. We're overcoming circumstantial barriers to get biogenic carbon sequestration improved in the natural landscapes, how to mitigate the spike of carbon when we make and consume stuff, how we control upstream ecosystems, how we improve the public health of our cities and specifically our building and building interiors. And how do we create incentives through our design process that incentivize the shift from economic extractivism to regenerative economic policy? And this means new materials and enterprise and employment for the people of the world. This is hard. This is one of those diagrams that you're not supposed to understand. The point is how confusing it is. This is called decarbonizing design. This is a set of design decisions that from a client or developer buying a piece of property through the design process with engineers and consultants to the contractor and all the trades, and then finally to the owner user. The decisions that you can make that will either emit carbon or store it. And some are way better than others. And it starts with the site. How many retaining walls do you have to put in your steep site? And how much soil will you displace and change? Again, this is really hard. But I'll put it to you this way. A history of carbon as it relates to us. 350 million years ago, forests started to develop in the middle Mesolithic. And in doing so, they produced suddenly an atmosphere on the planet that could allow biological organisms to develop. Forests produce the human species. Forests, we owe forests. We are a tree-dwelling species. Our ancestors started in trees. That's why we have thumbs that oppose our forefingers, so that we can climb and move. 350 million years by which high concentrations of atmospheric carbon were absorbed by these fast-growing plants. There was no biotic bacteria or fungus that existed yet. And so the trees grew, they died, they fell, they compacted, and they produced huge formations of hydrocarbon energy, future energy sources. 350 million years. 200 to 150 years, we've now learned to dig up that carbon, turn it into cheap energy, and burn it and pump it into the atmosphere. So if this is our carbon present, what's our carbon future? And I think it's all of the things we've talking about and all of the things that the professor is working on, which is biocircularity, waste circularity, and all of the new technologies that, yes, are really important. Photovoltaic arrays to energy production, wind farms, new material classes based on the existing material that we've already taken out of the planet to produce a future that is decarbonized, but that's also a habitable planet for us and also for species that inhabit the planet with us. And finally, the last thing I want to advocate for is we have to make this stuff really beautiful and compelling, because we're the ones that are making the argument to all the other people in the system who wonder why architects and engineers want to talk to forest scientists, or why architects and engineers want to talk to guys who work in landfills. We have to tell that story through our buildings and make them as beautiful as we can. And what that looks like, I don't know yet. But that's for all of us to figure out together. I'll close there. Thank you.
Vamos fazer um intervalo.
Algumas questões.
Primeiras questões, esta vez.
Thank you, Alan, for your splendid lecture. Algumas perguntas, por favor. Força, vamos a isto. Okay.
Não é melhor, Miguel, não é melhor com o microfone.
Obrigado. Alan, thank you so much. I have no words, and I'm very much ashamed because I'm very much engaged with the concrete lobby. My office, we always try to run away from the concrete lobby. We only had 2 buildings, maybe, that escaped from that very brutal economical system that we are engaged with. I'm not saying in Portugal, but in southern countries of Europe, we are very much engaged. In northern countries of Europe, maybe they are trying to change things. There are some changes going on now, but we have a lot of stress by the economical institutions, and but there is a paradox in your presentation, and you pointed out, which is the stress that forest will run if this system is properly achieved. Mm-hmm. And we have that problem now, not with building enterprises or building political, but with in industry political, because we are in Portugal and in Spain, northern Spain also, we are very much depending on an industrial system that occupied all the forests, almost all the forests, which is the eucalyptus forest. Mm-hmm. All the north of Spain and all the north of and central Portugal are were smashed with a forest by eucalyptus because of paper industry, because it has a lot of importance, meaning exports, of course. And I felt that same stress in Pyrenees, for example. We go to Pyrenees and we feel that it's such a lovely forest, but it's not, because it's most of it is spruce forest for industrial purposes, not paper, but for industry of wood.
Yeah.
And recently we saw a very brutal documentary around IKEA forests, and it's completely paradoxal, because IKEA is under a green label, but at the end it's a big lie.
Yeah.
They are destroying forests now in New Zealand. They arrived to New Zealand. So what can we do? This is the you just described a problem that transcends all the sectors in which we touch, and that's very important. And I'd like to answer each one individually, if I could. Take a little more time. I don't know how much time I have, but a little more time to try to address each of those. Because I have thoughts, I don't have answers. I have thoughts. The first overarching question is what you have described is a set of conditions that are produced by extractivism, right? For every forest, every big forest that you can show me in Iberian Peninsula in the US that has been devastated by economic activities that extract forests ruthlessly, as you say, I can show you a small forest that has been managed for regenerative health and that still produces fiber that we can use in buildings. It's just that we haven't adopted those techniques for forestry. I can tell you that the eucalyptus, if grown on degraded cattle raising land in southern Brazil, rather than in former Amazonian rainforest, will produce biodiversity and will produce fiber that can be used not only for temporary consumer products like paper, but actually for building. And we're working on adhesives that can use eucalyptus, these turboforests that grow so quickly. And I'll tell you that if you control how those forests grow and where they grow, you create an enormous carbon sink, you create a lot of material, and what's been proven by colleagues at mine at a real estate timber investment trust, BTG Pactual in Brazil, is that you also create incredible biodiversity quickly. And once those plantations have completed growing, the second growth that you plant has to be allowed to be invaded by indigenous forest. So you're actually creating an engine of afforestation, reforestation, which is really important. So eucalyptus isn't bad. It's just how we use eucalyptus or what it represents. Plantations aren't bad. It's just how we've done it in the past. These are all tools that we have to reconfigure. And I'll get to concrete now. And I don't want you to feel too bad, because I've built, even though I don't show them, I've built a lot of concrete buildings. There are many advantages to concrete. Concrete, when exposed to certain temperatures and humidities, mineralizes atmospheric carbon. It's part of the decay process of concrete. But that means that we could knock down a bunch of concrete buildings that we don't want anymore and spread out that material as paving, and it would actually absorb atmospheric carbon. But we also need it because we need things that we can bury underground that will support buildings and not degrade. And so, yeah, we'll need concrete for a while. So we need to keep working on concrete technologies to create carbon-carrying concrete or low Portland cement concrete. Those are all really important things that we need to do, and we need to work with the concrete industry, not in a pitched battle between timber and concrete, but to work with them to capture the benefits that truly exist in the use of this incredible material, reinforced concrete and cements. And also another partner in that equation. Our problem isn't that concrete is bad. Our problem is that it could be better, and that moreover, we just use it for everything because the concrete industry knows how to crank this stuff out. It's really easy to calculate for engineers. The builders are very familiar with it. But if you watch a concrete building being built on site, it's a ridiculous proposition because it takes a whole other building to create the formwork to make it. It actually is
incredibly thermally conductive, so that you have to actually insulate it to either keep it cool or warm, depending on the climate zone you're in. And it has to be filled in all around it with material that prevents the flow of air and the loss of internal ambient air quality. It's not that we don't want concrete. It's not that our steel workers need to give up at steel. We just need to stop the reflexive specification of those materials and to think more holistically about how the building can absorb material and also absorb carbon. That's what I would say. And I think once we solve that problem, we're going to be well on our way to solving all the other problems about human resource disenfranchisement, about biodiversity loss, and everything else. So again, it's a system problem. It's not a material problem. And so I'd like to take all of the challenges that you've raised, which are absolutely correct, and reconfigure the way we think about them as challenges. More as a synergistic approach to integrating the benefits and discarding the disadvantages. I hope that sort of covered it. And then we can talk a lot about building detailing to try to address some of the other problems. But thank you for that question.
Então podemos passar a... Não? Ah, ok.
Hello, Alan, excellent presentation.
Thank you.
I represent a social housing company from the town of Matosinhos in the north of Portugal, and we have not yet been able to give the step for sustainable building, but we are giving the first steps. We are much concerned about the energy problem, but sustainability is a bigger problem, and we are giving the first steps. But I think, from what I've learned from your presentation, that the answer perhaps is not just wood, but the combination of other technologies. We are, in that subject, organizing a panel discussion next month that brings together a contractor, a building company that has abandoned completely the traditional process of building and only builds with prefabrication and modular construction, a company that builds buildings of wood buildings or timber buildings, and a company that prints buildings with concrete, but also with clay. It can print a building with clay, and also a company of insulation materials, of cork materials, also out of a natural material. And the solution is a combination of all those technologies. So I would like to know your opinion about that.
Yeah, thank you. Well, a bigger thank you for doing the work that you're doing, because I think the question of social housing or deeply affordable housing is often the last thing we think about when we're building cities. It's sort of like a thing we feel we have to do. But ironically, I believe, you've just proved this to me, that the people who worked with me on the affordable housing project in New Haven, which is a former black church that represents a neighborhood that has been completely disenfranchised in the city, where area median incomes, there are really strong middle class families, but there are also people operating at 0% area median income. They're homeless, essentially. And this group has committed to creating 80 houses of mixed housing, 80 households of mixed housing for this people who are at risk of homelessness. And ironically, the person who is at the head of this group, like you, is trying to create affordable housing, primary goal, but he realizes the connection between this upstream benefit and all of the stresses that come from climate change, which are felt deeply by these communities, and realizes that the big real estate investors, unless they're hiring some very shiny architect with very shiny buildings, isn't going to be focused truly on this stuff. They're going to get LEED certification or BREEAM certification, but they're not really looking at the way that you are. It's kind of ironic that the people with the fewest resources, affordable housing developers, public housing developers, are doing this, and the market is not doing it yet. So I thank you. I think what you're doing is exactly right. There's no perfect combination of materials. It's all based on where you are and what's available and what does the least impact. So this is absolutely correct. But it is, as I say, ironic to me that the people with the fewest resources are the models for true sustainability, which starts to understand that if you don't make healthy buildings out of healthy materials that don't contribute to the problems, you don't create housing which is good for the people that we're building for. And I think that's less of a concern for contemporary capitalist development of buildings. And I wish it weren't so. I wish the really rich people were creating the models, but it's not that. It's the people who are really struggling for resources, because resource scarcity drives good behavior. I just think that's really a fact. I hate to sound like my Calvinist roots, but it is a fact. So thank you for your work. Sounds like it's perfect. I'd love to talk to you more about it.
Mais alguém?
Good afternoon. I only heard the last part of your exposition, unhappily.
Thank you.
But I'd like to pose you a question, because I think the theme is very important. What do you think about territory policies? The opposition, I think, there is between territorial policies and the aim you're talking.
Yeah. It's a really important question, and unfortunately, the worst possible outcome of this struggle, this debate between local self-interest and more global trans-systemic strategizing has been played out in the worst possible way in the United States, in my opinion, not to opine. What we're seeing is the triumph of self-interest and self-protection and the mythology that you just care about yourself and everything else will be fine, against this more, I think, open policy, because of a lot of failures by the people who are advocating more broad thinking, I'm afraid, in our country. So I'm feeling it very acutely right now in the United States. And I hope it's not the same for Europe. We look to Europe, always have, as a guiding light for social and environmental responsibility. When I speak to, I'll be very honest, when I speak to architects and people who are interested in the environment, I'm in safe territory. Everyone likes what I say. When I speak to people who work in the logging industry, who work in the construction industry, it's not so friendly an audience. And I'm aware of that. And they ask, and they're very polite, but they ask very pointed questions, which is, we're losing rural jobs. We don't have enough support. The regulatory systems that exist around environmental protection are way too complex. We can't get anything done. You're asking for housing. We can't get a project going in 10 years. How can we possibly do all this stuff? And it's all true. And so the answer is, we need really smart regulatory systems that try to understand where environmental protection is really critical and where it's just a sort of symbol. We don't need symbolic environmental regulation, which is, blankets everything with litigation and delay and cost. What we need to do is really understand what is a critical ecosystem, what is an ecosystem that sort of looks like a critical ecosystem but has already been highly disturbed. We need to generate funding that doesn't just make the richest people richer, but that builds local industries and local enterprise that will actually not only employ local workforces, but actually keep an eye on them so they're okay, because they're a valuable resource just like the materials that flow into that company to make products. So I think we have to tell our story really differently. And I hate to say it, it sounds superficial to say that it's a storytelling problem, but there are benefits for everybody all along the way, whether you're an ardent capitalist who wants to protect your company, or you're an environmental tree hugger who doesn't want to cut down any trees. There are a lot of complex stories that weave this together and that could potentially unite, as I say, a kind of rural, maybe perhaps more self-interested workforce, a generalization, I apologize, and this more sort of open-thinking urban world. I know that's a false dichotomy, but I do think they trend along those kinds of regional concerns. And I frankly think one perfect example is that the pollution that's coming from factories in Ohio, in the Midwest, is creating air quality problems in Connecticut on the East Coast. And the forest fires in Quebec, which burned 2 summers ago at an alarming rate, produced smoke so dense 600 miles to the south in my town that when you walked outside, it felt like you'd stuck your face in a barbecue grill. And I just think these are not questions that can be solved either in Quebec or in Connecticut or in Ohio or in California. And so how we construct something that is a little more effective than COP, which is highly symbolic, so that we can operate, again, regionally. I think that's the key. I really don't think, except in the very more extended way, that what I do in Connecticut will affect what happens in Japan. But I do think what I do in Connecticut will affect the northeast region of the US and the southeast region of Canada. And those economies can start to link up. And unfortunately, we've fallen into the trap, which is now we have tariffs that don't allow the flow of material back and forth between Canada and the US. So we've reversed the idea of regional policy development and bioregionalism, more importantly. So again, I think if we can tell the story in more complex and rich, nuances way and search for synergy rather than conflict, I think we're going to start to do that. And I can tell that story, this story, slightly differently to a different audience and know that I can have pretty much consensus. Circumstantial problems, but intrinsic consensus. And that's the important thing. I hope that was a long-winded answer. I apologize for that. Yeah.